So good afternoon and welcome to our, almost last lecture of the fluid mechanics course. Today, we're going to talk about computational fluid dynamics. So last week, we looked at experimental methods. Instead of going on an excursion to see the wind tunnel in Zurich, we did a formal lecture with some slides and showing you some experimental methods. And at least one slide in last week's lecture included a comparison between experimental methods and computational methods. And it was the idea to show to you that each way of each methodology of studying fluid mechanics, be it experimental or be it computational, has its pros and cons. Few things are easier in an experiment, a few things are easier when we do computations. I will have a similar slide today again, where we again look at the comparison, but most of what we're going to do today will be looking at an actual example of a CFD simulation, and to this end, we prepared this tutorial in COMSOL, and I hope that all of you had the chance to download and install a version of COMSOL on their laptops, and you also had a chance to take a look at the tutorial that we sent around. So the way this goes today, let me share my screen first. The way this goes is as follows. Let me start the slideshow. Yes, so here we go. Okay, so the way this will go today is that I will talk first for maybe about 30 minutes and give you a bit of an introduction into CFD, just say a few theoretical things, also a bit about the background, which hopefully will also be helpful if you use CFD tools. But then the main part will be the tutorial itself, or mostly Kai will walk you through this tutorial. It's meant to be interactive. We'll have to see how this works through Zoom, but the idea is that you can ask questions. You have time to do certain steps by yourself. If there is any problem, we can share screens and look at what's going on. Then finally, Kai will give you a homework assignment, which is essentially just another tutorial that you can work on with COMSOL. So with that, let me start on that first slide, which again is a comparison of computational fluid dynamics as one very popular method of studying flows, a comparison with experimental methods. One of the definite advantages of CFD being the acronym for computational fluid dynamics, is definitely the cost factor. And this is also the reason why a lot of companies like using CFD, because they at least think they can save money. And the main saving of money is that you don't need a wind tunnel facility. And setting up an experiment is relatively easy and can be done on a desk and does not require the same overhead that you would need to set up a physical experiment. Likewise, you do not have any size limitations as you have in experimental fluid dynamics. A lot of what we did last week was discussing how we can fit in a model of, let's say, a large commercial airliner into a wind tunnel, which maybe has a cross-section of, let's say, 3 by 3 meters. And we had to deal with all these similarity laws and the Reynolds similarity and scale down models and make sure the Reynolds number is maintained. These problems you do not have in computational fluid dynamics. It does not bother the CFD code if it is a large airplane or a small airplane. Well, it doesn't matter, of course, because the Reynolds number per se, but you don't have the size limitations. A third huge advantage is the diagnostic side. Last week, we looked at a few ways of measuring velocities and measuring pressures. And maybe you remember the term invasiveness. I pointed out that there are non-invasive methods of measuring velocities like PIV, and there are more invasive methods like a Pitot tube or a Prandtl tube, where you put a little probe into the flow, and of course that probe by itself will disturb the flow. Now in computational fluid dynamics, this problem does not exist. Once you obtain a flow field, a representation on a computer of a flow field, you can go and probe any value at any location at any time you wish without disturbing the flow. So by definition, anything you do is non-invasive. It comes at a cost. The cost can be high, can even be prohibitively high. For instance, if you need to save every flow field, think of a 3D flow field, for a long transient simulation, and you want to have a flow field stored, let's say every 10th of a second, you very quickly run into gigabytes, terabytes, even exabytes of data. And then the fourth point that I listed here, and by no way this list is exhaustive, there's a few more points. These are just the 4 points that came up in my mind when I wrote this list. The fourth advantage of CFD is that you're relatively free in modifying your experimental design. Think of a question where you want to understand the effect of viscosity in a certain flow system, right? You want to understand, for instance, you have a cardiovascular flow system, blood flow, and you want to understand what the effect of viscosity is. If the viscosity of blood increases or decreases, if this will fundamentally change something. Now in the CFD code, this requires you just to change a single number and does not really create any additional cost in modeling and finding new fluids. Whereas in an experimental and a physical experiment, you actually need to find fluids with different viscosities. Or what if you want to include gravity in your calculation or exclude gravity from your calculations? That's very simple in CFD. You can switch on or switch off certain effects quite easily. Whereas in an experiment, things are just there and you have to deal with them as they're there. Okay. So you're more free in tuning, fine-tuning your experimental design. Now, what about the disadvantages? I listed here 3 of them. Well, just as I had cost of setting up the experiment as an advantage, because you don't need the big wind tunnel, there's also disadvantage regarding cost, and it's the cost of running the experiment. One of the things that you will see if you run a physical experiment in a lab is that you need a lot of time to get the experiment ready to run, but once you run it, it usually takes very little time and especially very little cost. Right? You just run it and you measure and that's it. On a computer simulation, running the problem usually is very costly and requires a rather large, rather fast computer and can take hours, days, sometimes weeks or even months. Large-scale simulations, I will show you one or the other later on, or maybe I just switch back here. Like this simulation you see here, this is a jet, a turbulent jet. This took definitely several weeks, if not months, in execution time to simulate this on a big computer, on a supercomputer in Lugano. So the cost can be high for running the experiment, and whereas turning on the wind tunnel, it just goes. Then another disadvantage is certainly computational limitation. We will talk a little bit about discretization of governing equations later on. And you will see that you need a grid to resolve your flow field. And this all comes at a computational cost. The finer you make the grid, the more calculations you will need to do, the more multiplications and additions you need to do on the computer, and this quickly goes to the limit of a computer. I will make a few more comments on that later on. And then finally, the physical modeling itself. Whenever we do a CFD code, we require a set of governing equations, like Navier-Stokes. So as long as we accept that we have a fluid which behaves like a Newtonian fluid and the flow is incompressible, we're pretty safe with the Navier-Stokes equations, and that's not a problem. But what do we do if we have little particles in the flow, or if the fluid happens to be non-Newtonian? For instance, blood. We know blood to a certain degree is non-Newtonian. If you want to model this on a CFD code, you need to have a governing equation which describes the property of non-Newtonian blood. So this is a modeling which directly goes into the CFD code. If you run a physical experiment and you use real blood, you automatically have the correct rheology, the correct non-Newtonian behavior. Okay. So there's an additional modeling step that goes by default into any computational fluid dynamics investigation. So overall, the message is CFD is not just better than physical experiment. Neither are physical experiments always better than CFD. Both methodologies have their advantages and disadvantages. And it's the task of us as engineers to nicely balance the two methods, or maybe even use both methods and use them in a complementary way such that we get the best picture of the investigative process. So please keep that in mind. I mean, nowadays a lot of people think CFD is the new experiment, and in a few years we will not need experiments anymore, physical experiments. This is certainly not true. There's a few things only physical experiments can do, and there's a few things only CFD can do. Keep this in mind. Okay, so let's say we have selected or chosen to do a CFD experiment. Now we have been given a flow problem that we would like to understand. And I would like to go through these 4 steps here of running, or let's say of doing a full experiment. And you will see that the actual running of the CFD code is just one out of these 4 steps. In that case, here it is step number 3. Run the solver. That's the only real thing where you let the computer do the work. All the other steps are at least as important and usually take, well, maybe no more time, but also a significant amount of time. And well, let's look at that. Step number 1, problem definition. This is something you do without really turning on the computer. You first have to decide what type of flow are you looking at. You have to set or select a certain physical model. That's what I said before. You have to choose Navier-Stokes. And if you have particles in it, you have to choose equations which describe your particles. If you have certain material properties, certain rheology of the fluid, you have to choose the correct constitutive law for the fluid, and so on. So that's a step you have to do, and you have to do more in a CFD experiment than in a physical experiment. Then you certainly have to select physical parameters, right? Like viscosity, fluid density. It could also be that at the end you just choose a Reynolds number, which is sort of a combination of these values. That depends a little bit on the CFD solver. Many commercial solvers don't work with the Reynolds number. They ask you to actually enter physical quantity. This is more, well, because that's what people are more used to, and not everyone had a full education in what a Reynolds number really is. Third point, and maybe this ends up being one of the points which is mostly underestimated, it's the selection of boundary conditions, inflow and outflow, for instance. Of course, if you have a wall, if you have an airfoil, which is essentially a wall, there the boundary condition is relatively simple and easy, right? You have a no-slip boundary condition, and well, there's no ambiguity about it. But just as you have the issue of putting a little model of an airfoil, of a wing, in a wind tunnel, and the wind tunnel has walls, and these walls, if they're too close to the wing, they may affect the flow itself that you want to study. Just the same way you also have these problems in the CFD code, because the computational domain, the domain in which you solve your flow, which contains maybe a wing, is of finite size. Although you're not really interested in what's happening at the boundaries of your computational domain, there are still boundaries. And in reality, you would like these boundaries to be infinitely far away, or at least very far away. But of course, that comes at a cost. The bigger you make your domain, the more you have to pay for your simulation. So you want to make your domain as small as possible, but the boundaries as far away as possible, such that they do not interfere with the object you want to study. Selection of correct boundary conditions at these boundaries have a huge effect on the result. If you have a flow problem, for instance, you want to study the blood flow in the bifurcation of a carotid artery, your Halsschlagader, there's a major bifurcation here. There's a lot of plaque formation in there, and it's quite of some interest to do CFD studies in this section of the blood vessels. You usually just want to model a little section of the carotid artery, right? The incoming artery and the two outgoing arteries. But what boundary conditions do you set at the inflow and at the outflow? At the inflow, you probably need to set some velocity profile, which describes what the flow looks like as it comes from the heart. How do you know that? How do you know what the velocity profile is in the first place? Because that's actually what you would like to solve. The same goes for the outflow. The outflow definitely will be affected by what's happening in the brain. Now, you do not want to model the whole brain, you just want to model this little section in your neck. So selecting appropriate boundary conditions is very difficult, and usually, or not usually, but many, many times decides on the success or failure of your experiment overall. Finally, you have to select the geometry. Maybe straightforward if it's a technical object, you have technical drawings, CAD drawings. If it's a biomedical geometry, like a vessel segment, this might again pose some problems. You need image segmentation and many other things. So you already see even the problem definition without even having to turn on the computer can be quite lengthy and very difficult. Step number 2 is the mesh generation. This is usually seen as one of the most costly steps in a CFD experiment. This is where especially companies who do a lot of CFD or also structural computer models, that's where they see the most cost or time going into generating a good mesh. And we'll have 1 or 2 slides on that where I will discuss the problems of what makes a good mesh. You need to choose mesh width. You may need to locally refine the flow. You need to decide to have a structured or unstructured mesh. And eventually, you will need to choose your discretization schemes. So how do you translate your governing equations, which are usually partial differential equations? How do you translate them into something that can be solved with a computer? And this something which translates partial differential equation to an algebraic equation, usually a system of equations. This is the discretization scheme. And again, choosing the right one or choosing the wrong one means success or failure. Okay, and only then we come to the step of running the solver. Will take time. And then you get a result. But usually you're not done at this point when you run the solver. What is very important and often is forgotten is this loop here. You need to check for grid convergence. In the first place, you make a selection of a mesh or of a grid that you deem appropriate. You will have certain rules of thumb. But at the end, you will only know if your mesh or your grid is good enough if you run at least 2 simulations with slightly modified grids. So the classical way of doing it is you take one grid, you run the solution, and you refine the grid a little bit. Maybe you make a few more grid points, slightly smaller mesh width, and you run the result, the simulation again. Then you compare the results. If the 2 results are, well, then it will be identical, but let's say nearly identical, or at least for the research questions that you ask, sufficiently identical, then you know you have a converged, or let's say a good enough grid. Very often this will not be the case. And you will see there's a huge difference between the 2 solutions. That means you will need to further refine your grid, reduce the mesh width, and run simulations again. And then this iterative process you'll have to continue until you reach a point where modifying the mesh does not modify the result anymore. Then you know that your selection of a mesh is independent, or your results are independent of your selection of a mesh. That's the point you need to reach, and only then you can have a certain confidence in your results. Before that, they can be anything. Okay? That step is often forgotten, and it's an expensive step. So that's why people usually try to get by and not do it, but it's important. Point 4, we also discuss this real quick in a few minutes. Visualization of results and analysis is a post-processing step, but should not be forgotten. One of the issues, I mentioned it before, especially for 3D flow simulations, transient flow simulations, you obtain a lot of data. And having the data is nice, but being able to visualize, understand, and analyze the data can be a very difficult task, because you're dealing with, let's say, gigabytes or terabytes of data. And you're dealing with structures that are 3-dimensional and need to be visualized somehow on your 2D computer screen. So doing a good visualization of results can be very difficult. If you achieve that, one thing you need to do, and again, this is something that is often forgotten, you need to check for plausibility of results. This is the second blue arrow. One of the dangerous things of a CFD code is that it almost always, well, not always, but in many, many cases, it will just produce a result. And the result essentially is just a solution of the discretized equations. It's not necessarily the solution of your flow problem. There are cases, and maybe if we have the time, we'll get to that today, where the solver tells you, this is the solution, I believe, that is the correct solution of your problem. But if you check for plausibility, if you do certain, let's say, order of magnitude calculations with the background information you have, if you compare Reynolds numbers and typical results, let's say for canonical flows, let's say for flow around a cylinder, and you see, well, this result probably cannot be true, then you need to go back. You need to go back and check whether your problem definition, your boundary conditions, your physical parameters, or your physical model was really appropriate. So it's important not to forget that there are these steps in it. So you see the whole, a nicely run CFD experiment is far more than just running the solder by itself. Let's continue here. So what about the spatial discretization? I mentioned before the example of an airfoil. And we are interested in the flow around this airfoil. In almost any solver, not all solvers, I have a few examples of others, but almost any commercial solver will require something which looks like that. It's called a grid or a mesh, actually, which is used for the discretization of the equations. Essentially, it means that any point and these little triangular elements, these are little finite elements or finite volumes in which the governing equations are discretized. It's a level of breaking down the continuous partial differential equation into little sub-problems, let's say on the level of a triangle, where you can define the solution just by a finite number of values. So the finer you make this mesh here, and you see that close to the airfoil, you have a lot of little triangles, the more dense information content you will have, the better you will be able to resolve the flow. And farther away, like here, where we have large elements, we're not able to resolve that well, but of course the cost is much less, because like every little element is a certain number of calculations. So we carefully want to choose our grid, and especially here in this airfoil, you see that close to the surface of the wing, we have a lot of elements, a lot of little triangles, and that is mainly due to the boundary layer. At the boundary layer, we have high gradients, and we have these sharp gradients in the boundary layer, and to resolve these sharp gradients, we need a lot of points or not a lot of elements. Whereas farther away, the flow is relatively smooth and well behaved. Maybe here, with some hindsight from what we have learned, like on potential flow theory and around Yukovsky airfoils, we know that the velocity profile will almost be flat, right? Will almost be a parallel flow. So to resolve a parallel flow, you don't need that many points. You get by with just a few of them. So the mesh width, so that's the distance between 2 points in this mesh, which is typically denoted by h, is an important parameter, and it's up to you as engineers to choose the correct mesh width. And most likely, in the first shot, you will not choose the correct mesh width. You will have to iteratively go through that to find the optimal mesh width. Another decision you will see, and not every CFD code will offer you this decision, but those who do, I just want to explain to you, is the difference between structured and unstructured grid. So a structured grid in its simplest form is the one we see here on the left. This is a grid which is organized in a, let's say, logical way, like this here in a Cartesian way, where just by giving two coordinates, like coordinate I, row number I, and column number J, uniquely defines the point on the grid. In terms of computation, this is very beneficial. It lets you find data in memory very, very easily, and that makes computation very fast and very efficient. So it's more a computer science issue. Whereas in an unstructured grid, you need large lookup tables which connect the location or the neighbors of a certain element to each other. So you need lists whether, let's say, this triangle, where the neighbors of this triangle are. Right? You don't have like a simple Cartesian coordinate system on this mesh. So if you can work with structured grids, but I think the idea is clear why it's not always possible to work with them, because as soon as the geometry becomes complex, you cannot deal with structured grids anymore. Okay, so let's say we have selected one of these grids. So what's the next step? Next step is discretization. And usually, or in many cases, the CFD code does that for you. But very often you will have to, at least by a click on certain buttons, to select which scheme, usually it's called a scheme, which scheme is used to discretize that. And there's many schemes, and I have 2 slides to explain that. But let me just show you on one example what such a scheme could look like. Let's take the example of the finite difference method, a very popular method. And let's assume you have a derivative in your governing equation, like a df dx. And it could be, for instance, f could be the pressure, then this would be the pressure gradient. The pressure gradient in Navier-Stokes, first order derivative. So how can you discretize that? The easiest way to do that is by this finite difference. So you take the value at the location xj plus 1. So in this little scheme, this is the function f, and this is the point where you want to evaluate the derivative. So you take the value f at xj plus 1 minus f xj, so that's the value at j plus 1 minus the value here. And so it's the difference between these 2 values divided by the distance between these 2 values. So that's again this formula here. That's an approximation to the derivative here. And of course, you can do this, which is called the forward finite difference, if you take this point and the point to the right, or you can take it as a backward finite difference if you take this point and the point to the left. Which one is better? It depends. What is important to understand is that there's always an error attached to this. Of course, this is not exactly equal to df dx, it's just an approximation. And the error that you're making is of order h. What does that mean? It means the smaller you make your mesh width h, the smaller this error becomes. In the limit where h goes to 0, this becomes an exact representation of df dx. So is this a good approximation? Well, no, not really. It's a first order approximation. There's better ones. For instance, that one down here doesn't look that different. It's just fxj plus 1, so this point minus the other point divided by 2h. It's just a finite difference with the neighbor to the left and neighbor to the right. If you do the analysis, you will see that the error is much smaller. It scales like h squared. So that means if you double the number of grid points, so you reduce the mesh width by a factor of 2, the error here will be reduced by a factor of 2. In that case, the error will be reduced by a factor of 4, 2 to the square, 2 to the power of 2. Okay? So it's much more useful to use these methods here than that one. Okay? In general, there are many, many other ways of writing these differences, and they all have a certain error, which scales with a certain exponent p, and that p is called the convergence order. You might read this in the CFD code. And you have these coefficients here, which are usually defined in tables. You can also look it up on the web. These are the stencil coefficients. Just one example of discretization. There are other schemes, very popular ones, other than the finite difference scheme. The finite volume method, actually, this is probably the most popular scheme you find in commercial CFD codes. The finite element method, also extremely popular, not so much in CFD, but mostly in structural mechanics. And there's a few more. There's spectral methods and spectral element methods, which are probably maybe from a numerical sense the most sophisticated methods, but they're usually limited to non-commercial academic codes. But you may run across one of these methods. Then there's a set of methods, particle methods and singularity methods, which are special in the sense that they do not use a mesh. So instead of a mesh where you predefine a mesh where you discretize your points, they instead work with little particles which contain information, finite particles. You see this in this image up here. And you move the particles and each particle holds information in the flow field. So somehow your mesh or your particles are moving with the flow. Has certain advantages, has also certain disadvantages. SPH, very popular version of such particle methods. And there's singularity methods, Cannon method, fundamental solutions. And then finally, I would like to mention the lattice-Boltzmann method, which is a completely different concept of discretization. It goes into a more statistical concept of a Boltzmann gas. It doesn't directly solve Navier-Stokes, it approximates Navier-Stokes. A very nice theory, at first place rather complicated, but the beauty is that you can write very, very elegant and very short code. So those of you who are interested in that, visit this website, look at the codes there, and you will find that you can write a full CFD code 2D just on one page. It's really, really elegant. I mean, of course, if you go into details, it becomes also very complex, but they're really, really cool method. One more thing, we talked about spatial discretization. In practice, when you run a CFD code, you usually can also decide on the temporal discretization. It's similar to spatial, but some differences. Let me point that out. Let's assume we have our governing equation like that one here. Could be Navier-Stokes. So on the left-hand side, you have your du dt, like Navier-Stokes. Let's assume we put everything else to the right-hand side. This is just a large function or functional of your unknown u, of x and t, and it also holds some partial derivative operators, which of course for these, we use these schemes that we have just discussed, like finite difference steps. The question is now, what do we do with that one? And again, this is a differential, it's a derivative that we can discretize. Just as we can discretize the ddx, we can discretize the ddt. And again, the simplest scheme looks like that. It is called the forward-Euler scheme. It's almost the same as the first order finite difference that I showed you before. The velocity at the new, or the u at the new time step n plus 1 is equal to the velocity at the old time step plus delta t times the right-hand side. That's as simple as it gets. And many people use this scheme because it's so simple, because it's so simple to write down. But I can tell you, please do not use this scheme. Right? It's a very inaccurate scheme, and it's a very unstable scheme. It's cool to write it down for analysis and to understand what you're doing, but as soon as you want accurate results, stay away from forward Euler schemes. There's a backward Euler scheme that's much, much better, but forward Euler scheme or simply Euler scheme, stay away from that. Okay. There's very nice high order schemes, Hoyne, Runge-Kutta schemes, Adams Bashford have many names. They're usually much, much better, not much more cost, but more stability, more accuracy. Yes, backward order scheme just mentioned, Frank Nicholson. There's a long, long list of schemes. Usually they have all different kind of strange names. The only thing you really need to remember from this slide, stay away from that one unless you really just want to write it down on pen and paper. As soon as you use the CFD code, stay away from that one. Otherwise, you can run into troubles with accuracy and with stability. One slide on visualization. Keep in mind that visualization of flow fields is a difficult task, especially if we do 3D simulations, especially if we have unsteady flows, transient solutions. Streamlines are not useful. Streamlines can be easy to plot, but they can be very, very confusing or even misleading if you have an unsteady flow. Maybe you can use velocity vectors, quiver plots. Try to use particle paths. And we have looked, I think, second lecture on flow kinematics, the difference between a streamline and a particle path in an unsteady flow. CFD codes offer you usually the possibility to create particle paths. Use that. Then there's a bunch of vortex criteria. The most popular ones are the Q and the lambda2 criterion. You don't need to know too much more about these things, but these are, let's say, abstract metrics, abstract markers to define the localization of vortical structures. Can be very useful to produce meaningful pictures. We're now not really talking about precise quantitative analysis anymore. We're talking about visualizing flows, understanding flows. In 2D, it's a lot easier. If you just have a slice through a 3D flow field, velocity and vorticity plots can be very meaningful. Pressure plots, maybe not so much, but mostly velocity and vorticity plots are meaningful in 2D. 3D, they can become very, very misleading, or let's say at least difficult to understand. So let me finish it because we actually want to start with our tutorial. Just one last slide or one set of slides. Simulation of turbulent flows. I see many people showing me results of turbulent flows, and when I start asking them what they have done, they're convinced that they have solved for turbulent flow. And they're not really aware of what they have really done. And part of the problem is also that many CFD codes use a misleading labeling of what they're doing. So if you want to solve a full turbulent flow, which at a certain high Reynolds number, it will be turbulent, the real thing you can do, or the only real thing you can do, is to run a so-called DNS, a direct numerical simulation. That DNS solves exactly the Navier-Stokes equation. Nothing else, just solves Navier-Stokes and solves every vortex down to the smallest vortex at Kolmogorov scale. There are no additional models required with the DNS. Now we have seen how small these small structures can become, and that shows us immediately that the grids can be prohibitively large if you want to do a DNS of a flow at very high Reynolds number. A DNS of a full commercial airliner is completely impossible. Anyone who tells you otherwise tells you bullshit. It's not possible and will not be possible for decades to run a full DNS, meaning you resolve every single little sub-millimeter vortex on a whole commercial airliner. Just too large. Okay, but you can do it for smaller sections. You can do it for carotid bifurcation, for instance. perfectly possible, but expensive. So these are the expensive simulations. You solve Navier-Stokes without model. What most people are doing when they say they solve turbulent flows is this here, a RANS solution. It's a Reynolds average Navier-Stokes solution. We have written down the Reynolds average Navier-Stokes equations in our lecture on turbulence. What this equation does, it solves for the ensemble average of a turbulent flow. We're not solving for the turbulent fluctuations. It invariably will need a turbulence model to describe what the non-resolved small structures are doing. So in a RANS solution, you need much less grid points, but you need a turbulence model. And the model, as the name says, is a model, and the result will be as good as the model is. And the quality of these models is very limited. The third option you have is the large eddy simulation. We have not talked about this so far. Think of it as something between RANS and DNS. Or you can also think of it as something which somewhat under-resolves the DNS. It does not solve all the way down to the smallest Kolmogorov scales, but it solves not an ensemble average flow, it solves a real transient flow. Just to visualize the differences between these three concepts, let me show you my last slide with a bunch of examples. So this is a flow over a so-called backward facing step. Flow comes in from the left and goes on to the right, out to the right. And here you have this step which is going down. So you will get a flow separation here, and the flow becomes turbulent, and you get a reattachment here, and you get a bit of a turbulent flow structures all around here. Show you what this looks like. See the flow coming in more or less laminar. About here, it breaks down, very turbulent, and you have the recirculation zone here. Huh? This is a fully resolved flow. It's a DNS. This is pure Navier-Stokes. This is what comes out if you do an LES simulation. Much faster to solve, and I would say the quality is very good. Huh? Maybe there's some differences here in these structures, but at least from the bare eye, the results look very, very similar. Now let's see what happens if we do RANS. So what most people think is a turbulent flow simulation. Okay. See what you get? You get a solution which corresponds to the ensemble average of this flow. So RANS does what it promised to do, but by no means this solution shows the whole complexity of the full DNS flow, whereas LES does a pretty good job. Huh? I'm not saying not to run RANS, but whenever you run RANS, be aware of what you do. This is not turbulence, this is the ensemble average of a turbulence. Okay, so with that, I stop here. And let me stop the presentation. And we will continue with our tutorial. So what I will do, I will stop the recording, and I would like to ask Kai to get online to start looking at our tutorial.